Hey guys, I'm going to go over a commonly missed question from the quiz on Friday. I don't have the document camera to show you step by step with a pencil, otherwise I'd try to show it to you that way. So unfortunately I have to show like the entire answer key through the equation editor and the program that I use, and it's going to look really confusing, so I'm just going to do my best to use my mouse to go through each particular step. Okay, let's get started. Now, this was similar to the test. I may have changed some of the answers or numbers a little bit, but conceptually it's going to be identical. You've got this compound, silver chromate. It's sparingly soluble in water, which means if you put it in water, it might make a couple of ions here and there, but it's going to be in equilibrium where those ions could go back to being a solid. And it gives you this thing called the solubility of product constant, or the KSP value. It's a pretty small number. So it said, calculate the molar solubility of each ion in silver chromate. Okay, so here was step one. You've got to turn this symbol into an equilibrium dissociation equation, where it's going to break apart into its constituent ions, which is kind of what I showed you in this part right here. If you don't know how to do this, see me. You need to know how to do this, or else it's going to be a long day. The silver ion, we know, is a +1 charge, and that's because it's got a 2 subscript here, which tells me that there are 2 silver ions produced for every 1 chromate ion. No matter what, you're going to need the equilibrium expression in addition to this dissociation equation. So the equilibrium expression is shown right here. Since this is a solid, it can be omitted from the equilibrium expression. Usually it's products over reactants. It's not going to be the case here because it's a solid. So it's just, you won't see it. And the coefficients become superscripts or exponents. Okay, so there are 2 silver ions. That makes this a square term. This is just a 1. You just multiply it by concentration. So there's my equilibrium expression with the number. Now, I don't ever tell you guys to do this, but I guess in theory, if you wanted to, you could use an ice table. And so I did that here to show you why I'm going to use the values that I'm going to use. The solid can be completely omitted. I just have that grayed out. Don't need that at all. And since these will be produced, these should be positive values. Note how I have x times 2 to match that coefficient. So the silver ion equals 2x, and the chromate ion equals x. And those can be directly inserted into the equilibrium expression. And so now what I have is that KSP is going to be equal to 2x squared times x. Now that square term is going to make this a 4x squared times x, and I'm going to have this 1 times 10 to the negative 12th equals 4x cubed. I'm just going to solve for x. I divide both sides by 4, and that gives me this. And then I'm going to take the cubic root. If you wanted to, you could use the 1/3 power. Doesn't matter. All the same. And so I get the value of x. Now, what you don't need to do is go back and square x again. Once you get x, you could just put x into here. And that's kind of, I guess, the advantage of why I kind of like this rice table that accompanies the whole thing, because once you find x, you just, to find the concentration of silver at equilibrium, you just do x times 2. And so there, underlined here, I get my molar solubilities of each ion. Once you solve for x, you're done. Now, in part B, what happens if I add a strong electrolyte? For the purpose of this, expect that whatever you add to this sparingly soluble solid is going to be a strong electrolyte, where there would be no equilibrium expression. All ions would be produced when the solid is added. And so what I'm showing right below this molarity is the silver chromate, or sorry, the sodium chromate producing the sodium ion and the chromate ion. When sodium chromate is dissolved, it shares a common ion with the original silver chromate. And so the sodium can be disregarded. that's called a spectator. It just sits around. It's going to float in the solution. It's going to do whatever. It's not going to do much at all. A lot of things that are spectators are like nitrate salts, any group 1 and 2A elements like sodium, potassium, strontium, magnesium. Those typically are spectators just because they're going to participate very little with a lot of things. Now the chromate is a little bit more interesting because it's a common ion with the original material. And so the only thing that can go into an equilibrium expression, there's a couple things. When I say a couple things, I mean like exactly a couple things. You can put a molarity in there, or you can put a pressure in there. You can't put anything else in there. You can't put grams, you can't put volume, you can't put moles. Molarity is the only thing that goes in there. So what I did here is I took my 0.187 grams of the silver sodium chromate. I should use a different thing so it's not sounds so similar. I divided by the molar mass, and then I did this third step here is for every 1 mole of sodium chromate, I get 1 mole of the chromate. If that was a coefficient, it would change this number. And then I just divided by the volume. Now it was 250 mil. I made that 0.2500 liters. And that 0.0046 molar is directly inserted where the chromate would go. I don't have to account for the X and all this crap, because if you look, this 3.04 times 10 to the negative fifth is actually quite a bit smaller than the molarity of the chromate that was provided here. So its contribution, the silver chromate's contribution, is almost entirely negligible here. So all of the chromate that's going to be produced in this solution came from the strong electrolyte that completely dissociated and produced these two ions. And so from here, I just put in my number, and then I solve for silver, which is the silver ion. And look at our comparison. It's not incredibly easy to see, but it is about 6 times lower. Here, we had the silver concentration as being about 6.07 times 10 to the negative fifth molar, with the addition of only a very small amount of sodium chromate, and like 0.187 grams. That's like nothing. That's like a couple grains. I mean, if you saw that amount, you'd be like, what's this? It's nothing. So with the addition of a very small amount of a strong electrolyte that produces a common ion between the two compounds, my silver concentration decreases 6 times. It goes from about 6.07 to the negative fifth to about 1.15 to the negative sixth. That is called the common ion effect. The addition of a strong electrolyte in which a common ion is shared between the two compounds, one being a sparingly soluble salt and one being a strong electrolyte. And when I mean a strong electrolyte, I just mean that simply when that compound shown is added to water, all of its production goes to ions because it doesn't have very strong attractive forces for a number of reasons. Could be ionic radius. That'd be what I would say is the driving factor there. And also charge density. The sodium ion doesn't have a very high charge density. It's a +1. We'll get to all that. Well, we have already discussed all that. And so the common ion effect just simply says, based on Le Chatelier's principle, that if I add more concentration of one of the products in this case, the other one is going to have to go down in order for the KSB to be maintained. So hopefully that's helpful. We'll discuss this more later. I know it's not very easy to read when I show it this way, but that's how you're going to see it on an answer key. And I think next time, if I have a video, what I'm going to do is just show me writing it with the document camera. I think that'll be a little bit more easy for you guys to see. Common ion effect. You got to do all these steps right. It's a big headache, but it's really not that difficult when you know what steps to do.